guys, you better strap yourselves in because we're in for a bumpy ride. Now, why do I say that? Well, because in this lesson, we are going to be introducing ourselves to and investigating the properties of exponential functions in the form y equals a times b to the x plus q. Now, why do I say it's going to be a bumpy ride? Because I rate that this exponential function in grade 10 is the most difficult function that we get introduced to in grade 10. In comparison to the quadratic and the hyperbolic functions, which only have 2 parameters, exponential functions have 3 parameters that can affect the shape and position of the graph of the function. So we are going to investigate all 3 of those parameters, and for that reason, this lesson is going to be a little bit long. So if you only want to remind yourself about what one of the parameters does to the graph of this exponential function, skip to that particular parameter. Or if you just want to check out a summary of what all the parameters do to the graph of this function, skip to the summary at the end. But don't be lazy. If you're learning about exponential functions for the first time, work through this investigation with me, guys. Okay, we can do it. And with that said, let us investigate the properties of exponential functions in the form y equals a times b to the x plus q. Here it is, guys. Exponential functions numero uno, properties of exponential graphs with equation y equals a times b to the x plus q. There are those 3 parameters, a, b, and q. And obviously, this is known as an exponential function because one of the variables is an exponent, guys. Let us start with an introduction over here. Let me just move down a little bit. There we go. That's looking good. Now, in this lesson, we will begin exploring one of the new functions that are introduced in grade 10, the exponential function. The type of exponential function we will focus on in grade 10 is one in which the equation is in x and y. That means that we're going to see an x and a y in the equation, of course, with the x, whoopsie, let me try and make that neater, with the x variable as the exponent and the y variable as the subject of the equation. So that means we can simply expect y to be on its lonesome on one side of the equation, and the x is going to be an exponent, hence the reason we call it exponential functions. What can we also expect? Well, the graph will be an increasing or decreasing curve, but never both. And that increasing or decreasing curve will either go from being very shallow to very steep, or it will go from being very steep to very shallow. I'm going to show you what I mean by that just now when we look at these pictures of these graphs. The last thing we must expect, guys, is that the graph is restricted by what is called an asymptote, which is represented by a dashed line. So first and foremost, guys, let me point out what the asymptotes are over here, okay? Can you see these dashed lines? There's one of our asymptotes. There's another asymptote over there. Here is another asymptote over there, and here is another asymptote over here. And these are dashed lines that represent a value that the graph can approach but never equal. It never crosses over, it never touches these asymptotes. So these asymptotes restrict where the graphs are allowed to go. Let's check out our other stuff here. The graph is either increasing or decreasing, never both. Here is an example of what? This is a decreasing function, guys. As x increases, as we go to the right, y decreases, we go down. Whee! Like a little slide over here. But here is an example of an increasing function. As x increases, as we go to the right, y increases, we go up, okay? It's like having to climb some kind of crazy hill that sort of turns into a cliff over there. Here we have another example of an increasing function, okay? Looks a bit different, an increasing, maybe I want to try to spell that correctly. As we go to the right, as x increases, y goes up. And here is another type of decreasing function over here. As x increases, as we go to the right, y decreases, we go down. Okay. But now let's talk about this from going shallow to steep or from very steep to very shallow, okay? Guys, another word for shallow that we can use is a very gradual thing, okay? So a shallow incline is a gradual incline, whereas a steep incline is like you are climbing a cliff or falling down a cliff or something like that. So check out this graph over here. Starting from the left and going right, can you see this is very gradual? This is very shallow. And it goes, it's chilled, it's chilled, it's chilled. Whoa, we're getting steeper, we're getting steeper. Whoa, we're really steep over here. You can almost imagine yourself walking to the edge of a hill and you see the hill starting to dip like that, and you really don't want to fall at this point because you're going to fall, and then you're going to be suddenly tumbling down a cliff over there. And that is quite different in comparison to this graph, which going from left to right starts very steep, but then gets really gradual, really shallow over there. Think about climbing a mountain. You're climbing, it's really steep, you're climbing, it's really steep, but it gets to that point where it starts to even out a bit and becomes really easy and chilled until the point where you're just walking on top of the mountain now. So we can go from really shallow to really steep to really shallow, really steep to really shallow to really steep. Now let's have a closer look at the equation that we can expect for exponential functions over here, guys. Okay, here is the equation that we can expect. And this is known as the standard form of an exponential functions equation over here. Y is equal to A times b to the x, there's our variable that is an exponent, plus q. And we have three parameters. Parameter a over there, parameter b over here, the base of that exponent, and then we have parameter q over there. And in an exponential function, a, b, and q will all be real numbers, but there are some restrictions. Here's a restriction for a. A is not allowed to equal naught, because that would make for a very boring function, guys. It wouldn't actually be an exponential function anymore, because think about it. If this equaled naught, then naught times b to the x, that would just be naught. So suddenly we'd be left with y is equal to q, which is just a horizontal line. That's not an exponential function. But here is the really, really important restriction. B must be greater than naught. This base of the exponent is restricted to being only positive numbers for the whole of high school, guys. And that's because if you had a negative base over there, you would then technically not be able to draw the graph on the Cartesian plane, okay? Because you would not have something that is a defined real number for all values of x. But I'm getting technical now, guys. What's important is that you remember is that that base b is by definition restricted to be a positive value. Now it shouldn't come as a surprise, guys, that we call a, b, and q parameters as they influence the shape and position of the graph. Let's check out two examples of different graphs, exponential functions, which you can be expected to draw and work with in grade 10 and beyond. And these are different because of the different values for the parameters a, b, and q. They're a different shape, they're a different position because of a, b, and q. Okay, so let's have a little look at this guy on the left over here. There's the equation over there. The equation is y is equal to minus 2 to the x plus 3, okay? Now, what are the a, b, and q values for this equation over here? Well, some of you might already be thinking, Mr. Marie, you just told us that the b value has to be positive, yet I see minus 2 over here. Guys, what we actually have here is an invisible minus 1 times by 2 to the x. The x only applies to the 2 because it is only directly next to the 2. If I wanted to put minus 2 to the power of x, I would need to put it in brackets like this. And this is very different. It is not equal to minus 2 to the x because this x is only applying to the 2. So in this equation over here, b is actually equal to positive 2, a is equal to minus 1, and q is equal to a positive 3 over there. And this equation results in this graph over here. Check out our asymptote. Look at our asymptote over there. It's restricting the graph. The graph can't go past that asymptote, so it only lives below this asymptote there. There's a y-intercept, there's an x-intercept. It goes from very shallow to very steep, pointing downwards. It's a decreasing function that we have over here. And all of the things I've just described, they are the way they are because of these values, a, b, and q. let's have a look at this graphy graph over here. Look at this equation, guys. Very different to this equation over here. This equation is y is equal to 2 times by 1 over 3 to the x minus a 4 over there. Now, what are my a, b, and q values here now? Well, it's a little bit easier to see, I think. The a is a positive 2. The b is 1 over 3. And our q value is a minus 4. Okay. And because of all these parameters, we end up with this type of function. Notice that it's a decreasing function now. It goes from really steep to really shallow. Check out where our asymptote is, and check out the fact that the asymptote now restricts this graph from going any further downwards. Okay, so it exists only above the asymptote over there. So these are the kinds of graphs that we need to start being familiar with, and we are going to investigate how it is that these A, B, Q values over there result in the types of graphs that we are seeing. Now, where are we going to start in our investigation? We're going to start by exploring something that I have called the classic exponential function, y equals 2 to the x. Before we start investigating how the values of parameters a, b, and q affect the shape and position of an exponential functions graph, it is helpful to establish what the classic version of the graph looks like. Guys, I'm just calling this the classic version, okay? There's no universal agreement that we call y equals 2 to the x the classic one, but I'm going to call it the classic version because it's probably the most basic exponential function we get. And if we know what this looks like, then we can start messing around with the a, b, and q values and see what that does to the classic version, okay? So we're going to consider the classic exponential function as the one with the equation y equals 2 to the x, where the a, b, and q values are as follows. Well, let me remind you guys that the standard form of an exponential functions equation is y equals a times b to the x plus a q over there, okay? And let's compare that to y equals 2 to the x. Guys, there's an invisible 1 timesing by 2 to the x. A is equal to 1 over here. Boom. B is equal to 2 over there. And I hope you agree with me. There's an invisible plus 0 after the 2 to the x. In other words, our q value over here is a big fat 0. Okay. So we are going to investigate what this function looks like where a is equal to 1, b is equal to 2, q is equal to 0. Now, similar to what we did in grade 9, when we explored linear functions for the first time, we will use the equation of the classic exponential function to complete a table of values and plot the resulting coordinate pairs onto a Cartesian plane. So we're about to use this equation to complete this table of values here, guys. Let me give myself some space for working. Okay, so here's a value of x equals minus 4. I am about to use this equation over here, the equation y equals 2 to the x, to figure out what my y value is when I make x equals minus 4, and that will tell me a coordinate pair, a point on the graph for this function over there. Let's see what our working would be here, guys. Well, if x was equal to minus 4, then y would equal to 2 to the power of minus 4 over there. Oh, now at this point, it's really important that we remember our exponent laws, the ones that we learned in grade 9 in particular, where we learned that a to the minus n is the same as 1 over a to the positive n over there, guys. A negative exponent doesn't mean you're timesing by a negative number. It just means that you are writing a fraction in a fancy pants way. So you must imagine that there's this invisible fraction here, a to the minus n over 1, and it goes whoop to the bottom of the fraction, and the negative exponent changes to a positive exponent. So using that law, we should see that y is equal to 1 over 2 to the positive 4, which is 1 over 16. So for x is equal to minus 4, we know that y would equal to a very small value, 1 over 16. Now, these x values, they're going to work in a very similar way, guys. When I sub them in, we're going to have 2 to a negative power. We're going to flip it over the fraction line. We're going to see what our answer is. So I'm going to fill this in just now. For now, I'm going to skip to this interesting value over here, okay? This value here, When x is equal to 0, what does y equal? Well, y would equal to 2 to the 0. And again, we must remind ourselves about an important exponent law, that anything to the power of 0 is equal to 1. Well, anything that is except 0, okay? A is not allowed to be 0 here, because if you put 0 to the 0, you actually get something that we call undefined in mathematics. It's like dividing by 0, okay? You're not allowed to divide by 0 because it's undefined, just like you're not allowed to put 0 to the 0, that is undefined as well. But over here, guys, 2 to the 0, that's equal to 1 over there. So we have y is equal to 1 when x is equal to 0. Now, as our last little bit of something interesting to look at, I'm just going to divide that over there. Let us look at what happens when we, for example, sub in a positive value for x. Let's do positive 3. Why not? Okay. So if x is equal to 3, y would equal to 2 to the 3. That's really easy, guys. That's 2 times 2 times 2. That's equal to 8. Okay, so y will equal 8 when x equals 3. Now, we already have 3 points that lie on the graph of this function, okay? We've just figured out that there's a point minus 4, 1 over 16. We figured out that there's a point 0, 1. I hope all of you are suddenly thinking to yourselves, x value of 0. That means we've just figured out what the y-intercept is. The y-intercept is at 0, 1. We also know this other point here, which is 3, 8, okay? Now we could plot these right now and connect them with a nice smooth line, and it will be an exponential function. But because we're investigating, because we're going slowly, I'm going to fill out the rest of these y values nice and quickly. Why don't you pause the video and see if you get the same y values as me? Let's go. And there we go, guys. We have finished up our table over here. We have 9 points that we can plot and connect to draw the graph of this function. But before we do that, guys, while the above table of values gives us 9 points that we can plot onto the Cartesian plane provided below, it is important to see what happens to the function when we sub in certain values for y. Now, we should first notice that we can sub in positive values for y that are increasingly small, and we will still get a real answer for x. So these are y values that are increasingly closer to 0, and we'll still get a real answer for x. This means that the function with the equation y equals 2 to the x will be defined for these small values of y, and hence the graph of the function will exist for these values of y. Okay, so here are some values of y that are getting increasingly small. Here is y is equal to 1 over 32. And if you want to change that into a decimal, you'll see that this is 0.03125. So I think you'll agree with me, guys. That's a pretty small value right there. That's pretty close to 0. But it's not as close as y is equal to 1 over 1024. Guys, that is 0.000976, etc., etc. So guys, this is a really small value. It's really close to 0. But it's not as close as this value is to 0, guys. 1 over 32,768. That is 0.00003, etc., etc., etc. So I hope you agree with me, guys. These values are getting increasingly closer to 0. But when we sub these y values in, you're going to see that we still get an answer for x. Hence, we will have a coordinate pair, in other words, a point that we could plot on the Cartesian plane, and it would be part of the graph of this function. So let me show you this, guys. Let's sub in y is equal to 1 over 32. And we would get this, 1 over 32. Remember what we're subbing it into, guys. We are subbing it into this equation over there. So I'm subbing it in for y. So that's going to equal to 2 to the x. Woo! We have what is known as an exponential equation over here, guys. How do you solve an exponential equation? Well, you want to get it into the form a to the n is equal to a to the m, because if you can get it into this form where you have the same base on both sides, you can then make the conclusion, well, therefore n is equal to m. In other words, I want to take 1 over 32 and I want to express it as 2 to the something, because then I'll have 2 to the something is equal to 2 to the x, so that something must equal that x over here. Well, look how cleverly we do it, guys. We should notice that 32 is 2 to the 5. Oh my goodness. So 1 over 2 to the 5 is equal to 2 to the x. And then we use the reverse of the exponent law that I told you about earlier. 1 over a to the n is equal to a to the minus n over an invisible 1, guys. Let's use that over here. Oh my goodness. We should see here that 1 over 2 to the 5 is the same as saying 2 to the minus 5, and that's equal to 2 to the x. So what have we just discovered, guys? We've just discovered that x will equal minus 5 when y is equal to 1 over 32. In other words, we know that there's a point on this graph for this really small value of y, this value of y that's close to 0, that is minus 5 and 1 over 32. Okay? Now let me show you that this is still the case even if we get really close to y is equal to 0. And even if we get really, really close to y is equal to 0. Let me show you. So what I've just shown here, guys, is that even for these y values that get seriously close to 0, we will still get an answer for x. In other words, we will still get a point on the graph of the function. In other words, the graph still exists for these really small values for y. And we can keep going, guys. We can go to 1 over a billion, and you will still get an answer for x. However, when we sub in y equals 0 into the equation, we hit upon an issue. Okay, so when we sub in y equals 0, we will get 0 is equal to 2 to the x. And at this point, guys, I'm here to tell you that there is simply no value for x that will make 2 to that value equal 0. There is no solution for this equation, and that's because this equation is what is known as a false statement. No solution. There's no solution at all for x, okay? And it's because this is a false statement. It is not possible to get this. Now, for those of you smarty pantsers out there who suddenly grabbed your calculators and gone, what rubbish, Mr. Marie, I'm going to put 2 to a massively negative number. So if you start putting 2 to the minus 9,999,999 and press equals, then yes, your calculator is going to spit out 0. But the only reason your calculator spits out an answer of 0 is because your calculator can't even handle such a tiny, tiny number. So your calculator goes, whoa, that's a tiny number. I'm just going to throw out 0 at the person. Okay, so the calculator is being a bit naughty over there. Okay, go ahead, try it for yourselves, guys. Take 2, put it to a really large negative number. Your calculator is going to tell you that equals 0, but I guarantee it's not. It's just such a small number. It's so close to 0 that your calculator goes, it's so close to 0. I'm just going to say 0. Okay, so there's no solution for x. This is a false statement. Now, that's not the only value for y that we can sub in that causes a problem, guys. When we sub in negative values for y, we hit upon another issue. So, for example, guys, let's just say let y equal negative 2. Okay, let y equal minus 2. Look what happens here, guys. We would then get minus 2 is equal to 2 to the x. Now, once again, there isn't no solution, but for this equation, there is no real solution, guys, okay? And that means, yes, there is a solution that is a non-real solution. It is a solution that has an imaginary number in it. Now, I know that I'm almost sounding like I'm talking a whole bunch of nonsense here, guys, but if you go on to do AP Maths, or if you go on to do University Maths, you're going to learn about this absolutely mind-blowing thing in mathematics called the number I, which is defined as the square root of minus 1. No jokes. Think about that for a second, guys. When you're asking what is the square root of something, you're asking what must times by itself to get the value inside the square root. So think about what this is saying. This is saying, what is the square root of minus 1? What must multiply by itself to get minus 1? Think about that, guys. If you take any positive value and you times it by a positive value, what do you get? The answer is positive. If you take any negative value and times it by a negative value, what do you get? Whoopsie. You get a positive value. So how could there be anything that times us by itself to give us a negative? How can we get the square root of a negative? Well, we defined that as I over there. And the answer to this equation over here has an I in it. So it is a non-real solution, okay? Now, some of you might be going, well, why can't there be a real solution? How about if x was minus 1 over here? Because 2 times minus 1 is equal to minus 2. Well, yes, guys, 2 times minus 1 is equal to minus 2. But 2 times by minus 1 is very, very different. It's not equal to 2 to the minus 1. Remember what 2 to the minus 1 is, guys? That is simply a fancy pants way of writing 1 over 2 to the 1, which is 1 over 2. Negative exponents don't create negative values. It's just a fancy pants way of writing fractions. So there's no real value that can make this positive base 2 to that power equal a negative 2 over there. So there's no real solution. So we have two situations here. When y equals 0, we have an equation that has no solution at all. No real solution, no non-real solution. But when we subbed in negative values for y, we ended up with an equation which has no real solution. Okay, let me just quickly rub this out before we continue reading our lesson. Let's see what we are going to get to over here. From the above, we should see that there is no solution for x when we sub y equals 0 into y equals 2 to the x. In other words, the equation becomes a false statement when y is equal to 0. Furthermore, there are no real solutions for x when we sub negative values for y into y equals 2 to the x, but there are technically non-real solutions for x. Now, what does this mean? All of this means that the graph of the function does not exist when y equals 0 or when y is less than 0. In other words, when y is 0 or when we have negative values for y. With the asymptote specifically existing at the y value for which the equation of the function becomes a false statement. Super important thing over there, guys. The asymptote for exponential functions exists at the y value that makes the equation a false statement. Okay. Now, with all that said, guys, we're finally in a position where we're going to take our 9 points from up here. We're going to take these 9 points over there. We are going to plot them onto this graph over here. We're going to connect them with a nice curved line, a smooth curved line, and we're going to see the graph that we end up with. And that will be the first exponential graph that we are drawing together, okay? Why don't you do it at the same time as me, guys? Why don't you take these 9 points, plot them onto your Cartesian plane, see if you get the same points as I do and the same graph as I do. Let's go. Sure, I think you'll see that I struggled a little bit to get that curve nice and perfect over there, but there you have it. There is y is equal to 2 to the x, okay? It starts really shallow, it goes really steep, and I think you'll agree with me that plotting these points were a little bit tricky, guys, because the y values, they get so small that it becomes difficult to make sure that you're not actually just plotting y equals 0 over there. So for example, right over there, where I let the graph touch the y-axis, the x-axis, that's actually a little bit naughty because remember, guys, y equals 0 is our asymptote. Y equals 0 is the x-axis, okay? So the x-axis is our asymptote, and technically we should show that with a dotted line. Now, dotted line, I'm just going to draw it like this, sort of semi-under my x-axis over there so that you can see what's going on there, and I would then label that with y equals 0 as my asymptote. So check out my asymptote over there, a dotted line that is restricting my graph from letting y equal 0 or y be less than 0. Okay, so there we go, guys. That's what an exponential function can look like. And this is the classic exponential function, remember, where we have it in standard form, y is equal to a times b to the x plus q. And what did a equal? Well, a equals a very boring 1, b equals a very boring 2, q equals a very boring 0. Now, just before we start messing with these parameters, we must make sure that we see or note some important properties of this classic function over here, guys. Now that we have plotted the graph of the classic exponential function y equals 2 to the x, it is important that we notice some important properties about the graph. The graph has an asymptote at the x-axis, i.e. y equals 0. And as we should already know, guys, an asymptote is a line which a graph continually approaches but never touches or crosses. It should make sense that y equals 0 is the asymptote of the function, as can be seen by the fact that the graph of the function existed for increasingly small values of y, but as soon as we reached y equals 0, the equation of the function became a false statement and the graph stopped existing. That is what asymptotes show us, guys. The y value that we can get close to, but as soon as we hit it, the graph stops existing, hence why we have that dotted line over there. Okay. What else should we notice? We should notice that the graph has a y-intercept, but does not have an x-intercept, okay? This is for y equals 2 to the x. And the lack of x-intercept is because of the asymptote that lies on the x-axis, guys. Think about it. If the asymptote is the x-axis, in other words, if the asymptote is the x-axis where the graph is never allowed to touch it or cross it, then we're not going to have an x-intercept at all, guys. Finally, we must also notice that the domain of the graph is x is the element of all real numbers. Remember what domain means, guys? Domain is all of the x values for which the graph is defined, all of the x values for which the graph exists, while the range for this particular graph is y is greater than 0. Range is what y values the graph is defined for. In other words, which y values the graph exists for. The graph only exists for positive y values, y greater than 0. Now, while some of the above properties will remain the same for all of the exponential functions we face in grade 10, a number of the properties are affected when we change the values of parameters a, b, and q. And that's what we're going to do now, guys. We are going to see what the effects of the parameters a, b, and q are on exponential functions, starting with the effect of parameter a. So, guys, to identify what happens to the shape and or position of an exponential function's graph when we change the value of a, we're going to draw the graphs of 5 different exponential functions that have 5 different a values. Woo, guys, that is a lot of investigating that we are going to do. We will then be able to compare these graphs to each other and to the classic exponential function y equals 2 to the x, which will then allow us to make conclusions about how the value of a affects the shape and or position of the graphs. Okay, let's do this, guys. Now, we know from our work on the previous pages that the asymptote for y equals 2 to the x, where a is equal to 1, b is equal to 2, and q is equal to 0, is at the x-axis, i.e. y is equal to 0, and the table of values is as follows. Okay, so here's the table of values for y is equal to 2 to the x. That's what we completed earlier over there. Now what we're going to do is we're going to complete the table of values below for the equations y equals 3 times 2 to the x. Do you see what our a value is now, guys? Well, our a value is 3 over here. Think about it, guys. Y is equal to a times b to the x plus q. So over here, our a value is a positive 3. Our b value is the same. It's 2. Our q value is the same. It's 0. So the only thing we've changed is this a value, and we're going to see what that does to these y values. Hence, we're going to have a whole bunch of points. Hence, we're going to be able to plot this graph and see how it has changed in comparison to y is equal to 2 to the x. So let's do this, guys. Let's calculate some certain points over here, okay, together. So let's do the one where x is equal to minus 4. We did that one for the classic exponential function over here. Let's do this for our new function. What is y when x is equal to minus 4? But this is now for y is equal to 3 times 2 to the x, guys. So y would equal to 3 times by 2 to the minus 4. we should already know that 2 to the minus 4 is 1 over 2 to the 4, which is 1 over 16. So basically we have 3 times 1 over 16. And 3 times 1 over 16, guys, that's just 3 over 16. Interesting. Okay. So y is 3 over 16 when x is equal to minus 4. Let's actually do all the same x values that we did for the classic exponential function. So next we're going to do this x value over here and see what y is. I hope that you can read what I'm about to do here, guys. So y would equal to 3 times 2 to the naught. 2 to the naught is 1. We already know that. So 3 times 1 is just 3 over there. So that value is 3 over there. Okay? Whoopsie, Mr. Marie, you are being a silly person. This value is 3 over there. Okay. Let's just make sure we're nice and accurate like that. I think the last one we did with the classic exponential function was see what y was when x was equal to 3. So y this time will equal to 3 times 2 to the 3. We already know that 2 to the 3 is 8. So 8 times 3 is 24. Now, some of you smarty pantsers might have already noticed that we should actually really easily be able to work out the y values over here. And that's because the only thing that's new is this 3 times by the 2x. The 2 to the x is still the same thing, but we are now taking 2 to the x and multiplying it by 3. So then you should have noticed, oh my goodness, that just means that these answers that we have over here, they're all just 3 times bigger than what we used to have. Guys, check it out. We used to have in our classic version an 8 over here, a 1 over here, a 1 over 16 over there. Because what did we do? 2 to the 3, 2 to the naught, 2 to the minus 4. But now we're taking that 2 to the power and timesing it by 3. So every single time the answers are 3 times as big. 8 times 3, 24. 1 times 3, 3. 1 over 16 times 3, 3 over 16. So in that way, working out the rest of these y values should actually be really, really easy if we notice that they're just 3 times as big as what they used to be. And so there we go, guys. I quickly filled those in over there. I hope those are the same values that you got. Once again, I wrote these y values, these fraction y values as decimals, if that helps you plot the point. Sometimes I know people find it a lot easier to plot the point minus 1 point, or not minus, Mr. Marie, minus 1 and 1.5 versus minus 1 and 3 over 2. Okay, so if you find it easier to plot points that have decimals instead of fractions, that's why I wrote those up there for you. So there's all our points for the graph y equals 3 times 2 to the x. And we're not going to stop there, guys, by only looking at one equation where we've changed the a value. We are also going to look at this equation over here, y equals 1 over 3 times 2 to the x. Now, what have we done to this function over here? Well, I hope you agree with me, guys, that we can still see that b is equal to 2, that q is still equal to a naught, but now instead of a equaling to 3, now it's equal to 1 over 3. Now, guys, I will once again calculate the y value for these three x values, x equals minus 4, x equals naught, and x equals 3, like we have previously. But for those of you smarty pantsers out there who have noticed something, let me say this. Yes, guys, basically, you can just take the values from the classic exponential function, the values when y is equal to 2 to the x, and take those y values and do what to them? Well, you can times them by 1 over 3, which is the same as dividing them by 3 to get our new y values here. That's, after all that's happening here, guys. We're doing 2 to the x just like we did before, but then timesing that result by 1 over 3. In other words, dividing it by 3. Okay, for those of you guys who haven't noticed that yet, let's do those values manually over here. Okay, so this value over here, x equals to minus 4, y would equal to 1 over 3 times by 2 to the minus 4. We know that 2 to the minus 4 is 1 over 16, so this is 1 over 3 times by 1 over 16. That is 1 over 48, guys. That can be thought of as either 1 over 16 times by 1 over 3 or a third of 1 over 16. In other words, 1 over 16 divided by 3. 1/3 of 1 over 16, which is a really small number. That's 1 over 48. And yes, to you smarty pantsers out there, that's literally the same as taking 1 over 16 and dividing it by 3. Boom, nice and quick. What would have happened over here though? Well, over here, guys, we would have had y is equal to 1 over 3 times by 2 to the naught. 2 to the naught is 1, and 1 over 3 times by 1 is 1 over 3. Check it out, guys. In our classic exponential function, this was 1. But in our new exponential function, where it's 1 over 3 times by that classic exponential function, the answer is 1/3 of what it used to be. And over here, x is equal to 3. Well, let me maybe do this over here. Y would equal to 1/3 of 2 to the power of 3. 2 to the power of 3 is 8. 8 times 1 over 3 is 8 over 3. Okay, 8/3. In other words, a third of what it used to be over there. And with that logic, you should see that, oh my goodness, we just have the classic exponential function where all the y values are just times by 1/3. They're 1/3 the size of what they used to be. So we can fill out these values really quickly. And there you have it, guys. We have all our y values for those x values. So we have 9 points that we can plot. And these really tiny numbers I've written there, guys, once again, those are my decimals for all the y values, which are fractions, which is now all of them, because sometimes I find it easier to plot 4, 5.3 rather than 4 and 16 over 3. Okay, so what we should see is that while we have all the points we need to plot the exponential functions y equals 3 times 2 to the x and y equals 1 over 3 times 2 to the x, it's important to note that the graphs will also have an asymptote at the x-axis, i.e. y equals 0, and y cannot be negative. So that still is the case. Have a look, guys. So we had our function y equals 3 times 2 to the x, and we had another function y is equal to 1 over 3 times 2 to the x. And if we let y equal 0 in either of these equations over here, guys, we would get 0 is equal to 3 times 2 to the x. And then we end up with the same situation that we had before. This is a false statement. There's no value for x, either real or non-real, that can make this true. So there is no solution for x, no real solution, nor is there a non-real solution. And it's the exact same thing over here, guys. If we had to let y equals 0, you would see that 0 is equal to 1 over 3 times 2 to the x. We're left with a false statement. There is no solution for x. Okay. And the same is going to happen as happened before when we make y negative. We'll end up with something which looks weird, and it looks like a false statement at first, but it's not. It's an equation that can be solved, but using non-real numbers for x. Now, with all that said, guys, with acknowledging that the asymptote will still be at the x-axis, okay? The asymptote will still be at the x-axis, y equals 0, because that's the value that makes these equations into false statements. Let's take these points now. Let's plot them on our Cartesian plane over here. Please notice that our Cartesian plane already has y equals 2 to the x on it, okay? It already has y equals 2 to the x. And when we plot these new functions over here, we're going to see how this a value messed around with what the classic version looks like. Sure, and there we have it, guys. We have our new functions that have been plotted over here. We had the classic y is equal to 2 to the x over here, and here is our new function, y is equal to 3 times 2 to the x, and here is our other new function, y equals 1 over 3 times 2 to the x. Now, guys, once we have plotted the graphs, it should be clear from the above that the value of a can have the effect of vertically stretching or compressing the graph of an exponential function. Okay? Another way to describe the effect of a is to say that the value of a affects the steepness of the graph. Okay, so let me justify that by looking at how the change in the a value changed what was going on over here. So on our original classic function, when x was equal to 0, we had this y-intercept over here, guys. We had the y-intercept which was at 0, 1 over there. But now, when we changed our a value to 3, our y-intercept became 0, 3 over there. But when we changed our a value to 1 over 3, our y-intercept, now let me just be careful over here so that you can actually see what I'm writing. Our y-intercept, whoop, boom, over there became 1 over 3. And in this way, we can think about the a value as stretching or compressing. Okay, so the classic version is here. And when we made a equals 3, then the graph was stretched up until 3, okay? Stretched up to 3. But when we made a 1 over 3, it was squished, it was compressed down over there. And that counts for every single point on the function, guys. Remember when x equals, let's say when x equals 2. Originally, when x is equal to 2, that was when y was originally equal to 4. But when we changed a to 3, then when x equals 2, we ended up with, unsurprisingly, 12. Stretched 3 times as far as away from the asymptote as it originally was. 3 times further away from the x-axis as we originally had. So it's like someone grabbed the purple graph, y equals 2 to the x, and stretched it up, okay? Whereas in our other new function, y equals 1 over 3 times 2 to the x, this point over here would be the point x is equal to 2 and y is equal to 4 over 3. In other words, 1.3 recurring. So someone took the purple graph here, y equals 2 to the x graph, and squished it down to be 3 times closer to the x-axis. Squished it, compressed it down like that. Okay? And that's only one way that you can think of the value of a as affecting a graph. You can also think of the value of a as affecting the steepness of the graph. So check this out, guys. We had a graph that went from very gradual to very steep. But when a was equal to 3, it went from gradual to steep much quicker, guys. It was a steeper graph. And every single x value, the graph is already steeper than what it used to be. Whereas with a is equal to 1 over 3, it doesn't become so steep so quickly. It's more gradual for longer. So, in other words, every single point on this graph, y equals equal to 1 over 3 times 2 to the x, every single x value has a point that is less steep than what we originally had over there. So that's the 2 ways so far that we can think of the a value as affecting the steepness or the stretchedness, shall we say, the vertical stretchedness of an exponential functions graph. So let's look at the specifics. So more specifically, when a was equal to 3, the graph was stretched vertically, made steeper in comparison to when a was just equal to 1. And when a was equal to 1 over 3, the graph was compressed vertically, in other words, made less steep, in other words, made more gradual in comparison to when a is equal to 1. Now, guys, that's not the only effect that a can have. Please notice that we have looked at a is equal to 3 and a is equal to a third in comparison to a is equal to 1 over there. But these were both positive values. Now we're going to see what happens if we make a negative. Okay. We will now investigate the effect of having a negative a value. To start off, let's complete the table of values below using the equation y is equal to minus 2 to the x. Oh, yes, guys. This does have a negative a value. Where is this negative a value? But first, it will be valuable for us to clarify the values of the parameters a, b, and q in the equation y equals minus 2 to the x over there, guys. Remember, standard form, y equals a times b to the x plus q over there. Some of you might be thinking b is equal to minus 2. It's really not, guys. B is still equal to positive 2. A is the thing that is an invisible minus 1. What's actually happening here is we have y is equal to minus 1 times 2 to the x plus 0. So that shows that q is 0 over there. As I said earlier, guys, if you want to have the whole of minus 2 to the power of x, then I want to see your minus 2 in brackets. And that is very different to if we had minus 2 to the x. Because here the x is directly next to the 2. It only applies to the 2 and not the minus in front of it. Here the x is directly next to a brackets, so it applies to whatever is inside the brackets over there. Okay, so here's our first negative a value that we're going to explore. And we are going to see what our y values are. In other words, we're once again going to get a whole bunch of points for the graph of the function y is equal to minus 2 to the x. And once again, guys, let's do this typical old x values that we've always done. Let's look at x is equal to minus 4. Y would equal to, let's be careful here, guys, minus 2 to the minus 4. Okay, now at this point I am going to remind you about a really important exponent law, guys. We've seen it already, we've reminded ourselves already. A to the minus n is equal to 1 over a to the n. But I'm going to expand on this exponent law, guys, and I'm going to remind you that if we had a constant in front of a to the minus n, some kind of coefficient, for example, c times a to the minus n, then what would happen here is that the c would stay exactly where it was, okay? That minus power of n only applies to the a over there. So only the a would swap down to the bottom and become a to the positive n, whereas the c would stay at the top, c over a to the n over there. So whatever is not to a negative exponent stays on top of the fraction, just like what we have over here. Because what we have over here is minus 1 times by 2 to the minus 4. So that means that the minus 1 stays at the top, and that's over 2 to the positive 4 now. And that is going to equal, where are we going to do this? Dot, dot, dot. Where are we going to do this? Let me do it over here. Okay. Dot, dot, dot equals 2. Minus 1 over 2 to the 4 is minus 1 over 16. Okay. So we have minus 1 over 16 over there, guys. That is what our y value will be, minus 1 over 16 when x is equal to minus 4 in the equation y is equal to minus 2 to the x. Now, some of you smarty pantsers may have already noticed what's going on with that extra little minus 1 in front of our 2 to the x over there. But let's just keep going, guys. Let's keep going, because maybe some of you are going to notice when I finally do this with x equals 0 and x equals 3 over here. So let's check it out. X equals 0. Y would equal to minus 2 to the 0. 2 to the 0 is 1. 1 times by my invisible minus 1 over there, guys, is going to equal to minus 1. So it's equal to minus 1 over there. What was the y value for the original y is equal to 2 to the x? The original y value was 1. That's interesting. Now it's minus 1. What was the original y value for when we just had y equals 2 to the x? Well, the original y value was just 1 over 16, not minus 1 over 16. I wonder what that minus 1 is doing to all my y values, guys. Okay, so last but not least, over here, let's try x is equal to 3. What would happen? You would have y is equal to minus invisible 1 times by 2 to the 3. So that's minus 1 times by 8. That's minus 8. What do you know, guys? We have a minus 8 there now. That's different to the positive 8 we used to have when y was just equal to 2 to the x. So I hope by now some of you guys have noticed that clearly that minus 1 is just resulting in negative answers for y over here, guys. And that should make sense, because what is happening here after all, guys? We're just taking 2 to the x and every time timesing it by a minus 1. So we're doing what we originally had, 2 to the x, 2 to the minus 4, 2 to the 0, 2 to the 3, and we're timesing it by a minus 1, which turns it into a negative version of itself, guys. So with that logic, we should see that all these y values are just going to be the negative versions of what they were for the classic version y equals 2 to the x. So it becomes really easy to figure out these y values. And there you have it, guys. All of our correct y values. We have a whole bunch of points that we can plot onto a Cartesian plane, and we will then see what happens when we take our a, which used to be positive 1, and make it into a negative 1 instead. But first, While the above table of values gives us 9 points that we can plot onto the Cartesian plane provided on the next page, it is once again important that we see what happens to the function when we sub in certain values for y. Now with a less than 0, we should notice that we can now sub in negative values for y that are increasingly closer to 0, and we will still get a valid answer for x. This means that the function with equation y equals minus 2 to the x will be defined for these negative values of y that are close to 0, guys. And I think you will agree, we are just basically using the negative versions of the y values that we did before. So instead of positive 1 over 32, it's now minus 1 over 32, which is minus 0.03125. That's pretty close to 0, but not as close to 0 as minus 0.000097, etc. And that's not as close to 0 as negative 0.00031, etc., etc. So we're doing the same thing as before. We are subbing in increasingly small y values, increasingly closer to 0 y values that are negative, and we're going to see that these have an answer for x. In other words, that a point exists for these y values. In other words, that the graph of y is equal to minus 2 to the x exists for these really tiny y values that get closer and closer to 0 from the negative side. And there you have it, guys. We've shown that the graph will exist for y values that get increasingly close to 0 from the negative side. And we're basically setting up to show that even though we get really close to 0, the graph will still exist when we hit 0 itself. When y equals 0, we hit upon the same issue that we did when a was positive. Okay, let's do this, guys. So if we let y equal 0 in y is equal to minus 2 to the x over there, guys, then we end up with 0 is equal to minus 2 to the x. Once again, this is a false statement. There is no solution for x, no solution that is real nor non-real. That is because of the fact that this okie here is a false statement. This is literally not possible to get, okay? Now, that means that with y equals 0, making this a false statement, y equals 0 will still be our asymptote for this graph. And that shouldn't be too surprising, guys. We can get very close to y is equal to 0, but when y equals 0, the graph stops existing. Therefore, we have our asymptote over there. Now, how about positive values for y? We've only been subbing in negative values for y so far, guys. Because a is less than 0 now, remember a is minus 1, when we sub in positive values for y, we hit upon the same issue we had when we subbed in negative values for y into the equation with a is greater than 0. Let me show you what I mean, guys. So if we let y equal positive values now, such as let y equals positive 2. Look what we end up with, guys. We end up with 2 is equal to minus 2 to the x over there. Now, this isn't so much a false statement, but it's not possible to get this equation to be true with real values for x. It's not possible, okay? Let me show you that this is actually, in fact, the same equation as we had before when we let y equals minus 2 for y is equal to 2 to the x. We can divide both sides of this equation by minus 1. Why would we do that? Well, we would do that because of this. Boom, boom, right over there. So this ends up being minus 2 is equal to 2 to the x. That's the same equation as we had when we let y equals minus 2 for the equation y equals 2 to the x. That was when a was positive 1. And here, there was no real solution for x. No real solution for x. Okay, so the graph, in other words, is not going to exist for positive y values now that a is less than 0 in our function y is equal to minus 2 to the x over there. Now, guys, from the above, we should see that there is no solution for x when we sub y equals 0 into y equals minus 2 to the x. Furthermore, because a is less than 0, there are no real solutions for x when we sub positive values for y into y equals minus 2 to the x. This means that similar to y equals 2 to the x, the graph of y equals minus 2 to the x has an asymptote at the x-axis. In other words, y equals 0 is our asymptote. Now what I'm going to do, guys, is I'm actually going to jump a bit ahead, and I'm going to take this graph here, the points for y equals minus 2 to the x, and I am going to plot them onto the Cartesian plane we have for this purpose below. Okay, I'm going to plot them onto this Cartesian plane over here with my x-axis there, my y-axis over here. So here is our graph of the function y equals minus 2 to the x. I plotted all the points we had. I connect them with a nice curved line over there. And now this is going to give us an opportunity to see what these other graphs are going to look like in comparison to y equals minus 2 to the x. And remember, guys, for this one, it's just that a is equal to minus 1 for this function over here. And now we're going to change a to some different values and once again work out a whole bunch of points that lie on this particular function. Then we're going to be able to plot them down here, and we're going to compare them to what happens when a is just equal to a minus 1 over there. Starting with what we have over here, a being equal to what here, guys? Over here, a is equal to minus 3 over there, guys, and b is still equal to positive 2, and q is still equal to 0. And then we're going to get to an a value of what? This is when a is equal to minus 1 over 3, still with a b value equal to 2 and a q value equal to 0 over here. Now you smarty pantsers out there may be noticing that we have done two exponential functions that were very similar to these exponential functions. Up above, we did the function y equals 3 times 2 to the x, just like we did y equals 1 over 3 times 2 to the x. And we can use the results that we got for y equals 3 times 2 to the x and y equals 1 over 3 times 2 to the x to very quickly fill out this table of values over here. How are we going to do that? Well, let me remind you what happened when we simply made a minus 1. When we made a minus 1, we noticed that all the y values that we had for the classic function y equals 2 to the x. Where's our classic function? There we go. Here's our classic function y equals 2 to the x. When we made a equal minus 1, it basically was just taking minus 1 and timesing that by 2 to the x. In other words, whatever we had for 2 to the x previously, we times it by minus 1, and then we got our new answer for y is equal to minus 2 to the x. So all these y values were just made negative by timesing them by that negative 1 that we had for a. And now look what we have over here, guys. Here is the table we made for y equals 3 times 2 to the x, and here is the table that we made for y equals 1 over 3 times 2 to the x. Now, when we make this 3 a minus 3 and make this 1 over 3 a minus 1 over 3, the only thing that's going to happen is that all these y values will now be the negative version, guys. So basically what's happening here is instead of taking, for example, 1 over 16 and timesing it by a positive 1 over 3, now in our new function we would take this 1 over 16, which was 2 to the minus 4, and we'll be timesing it by negative 1 over 3, hence the answer will be negative 1 over 48. That's going to be the same for all the answers in our two new tables, guys. It's going to be the same y values, just negative, because the a value is the negative version of what we had up there. So filling out these tables is actually going to be really quick and easy. Yes, you could go about it the manual way. You can take x equals minus 4, sub it in over there, you'll get your answers for y, but guys, we're going to be efficient about it, and we're going to take our answers that we had for y equals 3 times 2 to the x and simply put a big fat minus in front of our answer, because that's the one big change that's happening over here, guys. Minus in front of the answer. Boom. Okay, so let's do this. So there we go, guys. There are all our y values over there for these particular x values for these functions, right? And I have once again drawn in the decimal versions of these y values, if that helps you plot them on the Cartesian plane that we have below. Let's do that, guys. Okay. Now, well, just before we plot our new functions onto this Cartesian plane over here, while we have all the points we need to plot the three exponential functions above, it's important to note that the graphs of y equals minus 3 times 2 to the x and y equals minus 1 over 3 times 2 to the x will also have an asymptote at the x-axis. In other words, at y equals 0, and y also cannot be positive, similar to y equals minus 2 to the x. Let me just show you that we'll have our false statements at y is equal to 0, guys. Okay, so let's go ahead and see that if we make y equal 0 in this equation over here, then we would have 0 is equal to minus 3 times 2 to the x. And we can, if we choose, divide both sides by minus 3 as though we were trying to solve for x. So then we would get 0 divided by minus 3 is 0. And then minus 3 times 2 to the x divided by minus 3 over there, boom, boom. We would just get 0 is equal to 2 to the x, which is once again a false statement. It's not possible. No solution for x. Just like if we let 0 equal minus 1 over 3 times 2 to the x over there, okay? And if we for example, times both sides by minus 3, look what would happen here, guys. Well, minus 3 times by 0 is still 0. Minus 1 over 3 times by minus 3, that's a positive 1. So we just end up with positive 1 times by 2 to the x, which is 2 to the x. And both of these guys have no solution for x. Not real or non-real. No solution for x at all because they are false statements. Hence, our asymptote will still be at the x-axis, y equals 0. Now, with that acknowledgement there, let me go ahead and plot these functions, guys. I'm going to plot these two new functions, and then we're going to be able to see what these negative a values did to our function. And there you have it, guys. There are our three functions plotted onto this Cartesian plane. Let me move up a little bit like that, okay? This guy over here, that is y equals minus 2 to the x. That's what happened when we had a is equal to minus 1. Here is y is equal to minus 1 over 3 times 2 to the x. That's when a is equal to minus 1 over 3. Here we have in blue, y is equal to minus 3 times 2 to the x. That's when a is equal to minus 3. Now, once we have plotted the graphs, it should be clear that a negative value of a results in exponential functions that point downwards now, guys, and they only exist below the asymptote, which is opposite to when a was greater than 0. Okay, so that's one really important big difference that happens when a is less than 0. The graphs are below the asymptote and they point downwards like that. Now, more specifically, something very interesting has happened here, guys. We should notice that the graphs with a values, minus 1 over 3, minus 1, and minus 3, are the reflections in the x-axis of the graphs with a values 1, 3, 1, and 3, 1 over 3, 1, and 3. Yes, that's right, guys. These graphs are basically the same as the graphs that we had up here. Let me find where we are here, guys. There we go. They're basically the same as these three graphs over there. It's just that this x-axis has acted like a reflection. This x-axis has acted like a mirror, and these graphs are reflected in that mirror to become what we have down over here, these graphs over here. That mirror is the x-axis, in other words, the asymptote. And if we had them lined up, in other words, if we had all these graphs drawn on the bottom half of a Cartesian plane and all the graphs with the positive a values on the top half of the Cartesian plane, you would see that they would be totally symmetrical about this line, about the x-axis over there. In other words, the x-axis is the reflection. It is, well, these graphs are the reflection of each other over the x-axis. Okay, what else should we notice? Well, we should also notice that similar to the different positive a values that we looked at above, negative a values can also have the effect of stretching or compressing an exponential function vertically. Guys, let's just quickly have a little look at that. Okay, so please notice that when we had a equaling to -1 over here, we had the sort of negative version of the classic function, the reflected version of the classic function. But then when we made a -3, then we took every single point that was originally on y equals -2 to the x, and we stretched it 3 times further away from the asymptote. Stretched it 3 times further away. However, when we had a was equal to -1 over 3, that was when we compressed. Everything was compressed, squished down 3 times closer to the asymptote, 1/3 of the distance away from the asymptote now. So the a value, not only in this case because it was negative reflected over the x-axis, but it also stretched and compressed our exponential function vertically. In other words, it changed the steepness of our function. Okay, so the more negative we went, the steeper our function got more quickly, whereas the less negative, in other words, an a value closer to 0, made it that our graph didn't get as steep as quickly over there, similar to the positive a values. Now guys, with all that said, let's summarize what we have learned about the influence of a parameter a on the shape of an exponential functions graph with the equation y equals a times 2 to the x. In other words, when b is equal to 2 and q is equal to 0 in y equals a times b to the x. So this is basically a disclaimer. This is saying we're going to make some conclusions about what a does, but this is very specifically for what the parameter a does to this graph, y equals a times 2 to the x, where b is specifically 2 and q is specifically 0. Okay, in this equation y equals a times b to the x plus q. Let's talk about the effect of parameter a. What have we noticed? Well, we noticed that if a is positive, i.e. if a is greater than 0, we noticed that we can expect a graph that points upwards like this. Boom, and it goes very steep at a certain point, okay? So if a is positive, we end up with a graph that points upwards. It lives above the asymptote over there, okay? And actually, I'm going to go ahead and I'm going to draw this in a different color. I'm going to draw it in purple like that. You'll see why I do that just now. Okay, so there we go. It lives above the asymptote when a is positive. However, when a is negative, we have a graph that's going to point downwards and it's going to live below the asymptote over there. Okay, so let's summarize this, guys. It will point upwards is basically what we are saying. In other words, it will be above the asymptote. Here will be our asymptote over there, and it will be above the asymptote every single time. Whereas if a is negative, you can expect a graph that is going to point downwards, okay? In other words, it's going to live below where the asymptote is, below the asymptote every single time. Okay, now, what did we see happened when we changed the sign of a? In other words, when we made it, when we took it from positive to being negative or negative to being positive. Well, guys, we saw that simply taking the a and changing the sign of it, so from 3 to -3, or from -1/3 to +1/3, what does that do to the graph? That reflects the graph. It reflects the graph over the asymptote, over the asymptote. Okay, so the asymptote is basically an axis of symmetry, a little reflection, a little mirror when we change the sign of a. And how about this, guys? What else does a do? Well, the value of a can stretch or compress vertically. So it can vertically stretch or compress, stretch or compress the graph. Oh, wow, whoopsie, I see I have vertically over there. Okay, let me take away vertically because I'm going to replace it with a fancy word that means stretch or compress. And that fancy word is dilate, okay? It can dilate, i.e. stretch or compress the graph vertically relative to when A is equal to plus or minus 1 over there. In other words, guys, we can think of the value of A as determining the steepness, or how gradual, rather, the steepness of a graph. Okay, there we go. Not quite sure why we have all that space over there. I think that over here I was going to draw what I'm actually going to draw over here, okay? Because over here, I'm going to say that these are examples of when A is equal to 1, or when A is equal to minus 1 over there. Whereas now, let me draw for you what happens when we, for example, make A more than 1 over here. Woo! Whoa, Mr. Marie, that is so nasty. So we go boom over there like this. So this would be when A was greater than 1 over there. Whereas over here, if we had something that was squished down like this over here, this would be when, not when A is only less than 1, okay, but when A is less than 1 but still greater than 0. In other words, still positive, okay. So that's what we can expect over there. But when A is negative, this is when A is minus 1, and this would be boom when A is less than minus 1. For example, i.e. when A is equal to minus 2, okay, that's less than minus 1, and that's stretched vertically like that, dilated like that. Whereas this would be an example of what the exponential function would look like if we had A that was greater than minus 1 but still less than 0. So some kind of fraction value that is between minus 1 and 0 over there. And there we go, guys. How chilled is that? That's all the things that A can do. That's one parameter down, 2 more to go. Here we are going to look at the effect of parameter B. Now remember, guys, B is only allowed to be positive in exponential functions of the form y equals a times b to the x plus q. To identify what happens to the shape and or position of an exponential functions graph, when we change the value of b, we are going to consider the graphs of 4 different exponential functions, namely, okay, y is equal to 2 to the x, y is equal to a half to the x, y is equal to minus 2 to the x, and y is equal to minus a half to the x. Okay, now for these graphs over here, what are we looking at? We're actually technically looking at only 2 different b values that are combined with 2 different a values. For all of these graphs, q is just equal to a boring old 0, okay? But for 2 of these graphs, a is equal to a positive 1, whereas for the next 2 graphs, a is equal to minus 1, okay? And then the b value that we're investigating is as follows. Over here, we have a b value of a positive 2, but over here we have a b value of a positive a half. Here we have a b value of positive 2. The a value is what's negative, guys. And here we have a b value of positive a half over there. Okay, so it should be clear that we are investigating the effects of parameter b on exponential functions by using the values b equals 2 and b equals 1 over 2 in 2 different circumstances, when a is equal to 1 and when a is equal to minus 1. The graphs of y equals 2 to the x and y equals minus 2 to the x have already been plotted on the Cartesian planes provided below. And guys, these are the classic version and the negative version of the classic version, okay? And we're not going to plot them again because, my goodness gracious me, we plotted them above. And once we have also plotted the graphs of y equals a half to the x and y equals minus a half to the x, we will be able to make conclusions about how the value of b affects the shape and or position of an exponential functions graph. So the new graphs that we're going to plot are these two. So we're going to figure out the table of values for these two exponential functions over here. Let's start by considering the two functions that have a equal 1, a positive value for a. So we should expect these graphs to be above the asymptote and they'll point upwards. We know from our work on the previous pages that the asymptote for y equals 2 to the x is the x-axis, and the table of values is as follows. Okay, so this is well established by now, guys. Asymptote, x-axis, in other words, y equals 0. It was y equals 0 that made this equation a false statement. Hence, that was our asymptote over there. And there are all our y values for the x values. And in fact, here is y is equal to 2 to the x plotted on the Cartesian plane already. How nice, okay? Now, let's complete the table of values below using the equation y equals a half to the x. Woo! Now with this new b value over here, guys, b equals a half over there, I'm once again going to revert to figuring out 3 of these points manually. I'm going to sub in x equals minus 4, x equals 0, and x equals 3 into this equation, and we're going to see what the results are, okay? And then we're going to see if there's any way we can see what the rest of these results are by being smarty pantsers. So here we go, guys. What does y equal when x equals minus 4? Well, y will equal 1 over 2 to the minus 4. Now, at this point, I need to remind everyone about an important exponent law. And that exponent law is if you have a over b to a power of n, then you must apply that power to the numerator and the denominator. A to the n over, whoopsie, not a, Mr. Marie, over b to the n over there. Okay, so basically what's happening here is that this will equal to 1 to the minus 4 over 2 to the minus 4. And as we know from exploring the exponent law about negative exponents earlier, this is the same as 2 to the 4 over 1 to the 4. Hello, flip them around the fraction line, the exponents become positive. 2 to the 4 is 16, 1 to the 4 is 1. Oh, so that's just equal to 16. That's interesting. Our y value here is 16. Okay, that's interesting. Now, how about our y value for x is equal to 0? Let's do this, guys. So y would equal to 1 over 2 to the 0. Anything to the 0 is equal to 1. Okay, so 1 over there. Okay, so that's exactly the same. Interesting. Well, how about our last little okie over here? X is equal to 3. Well, what we will do here, where are we going to do this? Let me do this right over here. Okay, so x is equal to 3. Therefore, y would equal to 1 over 2 to the power of 3. That's 1 to the 3 over 2 to the 3. That is 1 over 8. So we end up with 1 over 8 over there. So we had 1 over 8 when x is equal to 3 now. But look what we had when x is equal to minus 3 over here. That used to be 1 over 8. Now, this is no coincidence, guys. This is the effect of taking a base, which used to be 2, okay? A base which used to be 2, and getting the reciprocal of it, flipping it over. Think about what 2 is, guys. 2 is the same as 2 over 1, and if you flip it over, if you get the reciprocal, that gets you a 1 over 2, okay? What happens is that the negative x values that got you certain y values, those y values are now achieved with the positive versions of x, and these y values that we got with these positive x values, these y values will now be achieved with the negative x values over there. So for you smarty pantsers out there that noticed that, guys, you will be able to see here that the next value here would be 8, just like this will be 4, just like that will be 2, just like this will be a half, a quarter, and 1/16 over there. Now that means that we have all the points that we need to plot y is equal to a half to the x over there. But before drawing the graphs, it's important to note that the function of y equals a half to the x also has an asymptote at the x-axis, i.e. y is equal to 0. Let me prove it to you guys. If we let y equals 0, you would get 0 is equal to 1 over 2 all to the x. This is a false statement because there is no solution for x that can make this true. It's impossible. No real nor non-real solution for this. Okay, so let's go ahead and plot this graph now. We're going to plot this graph now. Plot it along with me, guys. Let's see if we both get it right. Now, once we have plotted the new graph, it should be clear that the graph y equals a half to the x is a decreasing function in comparison to the increasing function of y equals 2 to the x. Check it out, guys. As x gets bigger, y gets smaller for y equals a half to the x. In comparison, for y equals 2 to the x over here, that's an increasing function. It's going up. Y is going up as x goes up over there. So that's a major change. Yes, they're both still above the asymptote, which I have very naughtily not drawn in over here. Let me just quickly draw in my asymptote over here. So yes, they're both above the asymptote. Yes, they're both pointing upwards. That's because their a values are positive. But here, with 2 to the x, increasing function, gradual to very steep. But with a half to the x, it goes decreasing, very steep to very gradual. Now, why does this happen, guys? This change is because of the difference between multiplying a number greater than 1 by itself and multiplying a number less than 1 by itself. There's a big difference when we do those things. And let me show you what I mean by this, guys. Okay. To understand this, let's consider what happens when we multiply the number 1 by itself any number of times. I hope you agree with me, guys, that it doesn't matter how many times you times 1 by itself. 1 squared, the answer will be 1, okay? 1 cubed, the answer will be 1. 1 to the 5, the answer will be 1, especially if I draw that 5 as an actual exponent. Guys, you can take 1 to the 1 million and the answer will be 1. No matter how many times you multiply 1 by itself, the answer stays exactly the same. It is still just 1. Now, let's compare that to what happens when we take any positive number less than 1 and multiply it by itself any number of times. Let's look at what happens with the number half, for example. That's, after all, what we used over here. We have a base of a half for y equals a half to the x. And when you change the value of x, you are changing the number of times you are multiplying a half by itself, guys. So let's investigate closely what happens when you take a half and times it by itself. Okay, I hope you agree with me, guys, that if I had to write for you a half squared over here, that is the same as saying a half times by a half, okay? And we shouldn't be surprised by the fact that the answer is 1 over 4. The answer is a quarter. Now think about that just for a second. A half times a half, what does that mean? Times is another word for of. You want to see a certain amount of a certain value. Here, I want to see a half of a half. So I only want to see 1/2 of something that's already a half. And a half of a half is 1 over 4. Now the big thing I want you to notice is this. When we times the number that was smaller than 1, but still positive by itself, the result was smaller than the number we started with. We took a half, we times it by itself, the result is smaller than a half. It's less than that number that we started with over there. And that happens no matter how many times we multiply a number less than 1 by itself. So for example, let's take a half and put it to the power of 3 now, okay? So now we're not timesing a half by half. Now we're timesing a half by a half by a half. So I want to see a half of a half times a half. Do you see what I mean there? So that's why it should be no surprise that this answer is 1/8. We want to see a half of a half of a half. That is 1/8 over there. So interesting. The more we multiply a number less than 1 by itself, it looks like the smaller the result is becoming. Because over here, we just multiplied a half, well, we just squared a half over there. We got 1 over 4. But then we cubed a half, we got 1 over 8. Let's see if that keeps happening. Let's put 1 over 2 to the power of 5. Now we're seeing a half of a half of a half of a half of a half. And that is 1 over 32. So it seems to be continuing. The more we multiply a number less than 1 by itself, the smaller the result, guys. And we can even get to an extreme number or an extreme power. And let me quickly just do this. I quickly want to group everything a bit closer together over here. 1/2 to the power of 2, that's 1/4. And we did 1/2 to the power of 5, didn't we? That was 1/32. Let's do 1/2 to the power of 10. That's 1/1024, okay? So that's a lot smaller than what we started with, but that's because we've times the half by itself many times over there. Okay, well, that's what happens with a half, okay? That's a small number that's less than 1, but still positive. How about like a really small number less than 1? How about, for example, like 1/100th, okay? 1/100th. In decimal, this is 0.01. So I'm going to take 0.01 and I'm going to square it, okay? What you end up with, oh, whoopsie. I'm not going to do 1/100th, guys. I'm going to do 1/10th. How about that, okay? And 1/10th is 0.1. Now, if you take 1/10th and you square it, you end up with 1/100th. Now, that is smaller than what we started out with. This is 0.01, okay? So we took a number less than 1, but still positive. We squared it. The result was smaller than what we started. Well, let's see if the result gets even smaller when we take 1/10th and we times it by itself even more. So let's take 1/10th and cube it. Oh, what do you know? We end up with 1/1000th. That is 0.001 over there. So the trend is continuing. And the more we multiply 1/10th by itself, the smaller the result is going to become. So as you can see here that I did really quickly, guys, 1/10 to the 5, that's 1/100,000. Whereas 1/10 to the 10, that is 0.901. Okay, so that is continuing the trend. Now, I've taken half, I've taken 1/10th, but now how about a number that is smaller than 1, but only a tiny bit smaller than 1? How about we take the number 99/100. 99/100. In decimals, guys, this is 0.99. So that is less than 1, but my goodness gracious, it's very, very close to 1, okay? And let's see what happens when we take this number that's just a tiny bit less than 1 and multiply it by itself. Let's see what happens with the results. So the trend continues. When you take a number that's less than 1, even if it's a tiny bit less than 1, and you times it by itself, the result is smaller than what we started with. And the more you times it by itself, the smaller the result gets. Now, keep that in mind, guys. Keep that in mind, and keep in mind the fact that if you have a number 1 and you multiply it by itself as many times as you want, that just stays as 1. But a number less than 1 multiplying by itself becomes smaller and smaller and smaller. Whereas, let's compare these results to taking a number that is bigger than 1 and multiplying itself an increasing number of times. And we've already done this with the number 2, guys. We already know that 2 squared is 4, and that 2 cubed is equal to 8, and that 2 to the 5 is equal to 32, and that 2 to the 10 is equal to 1024. But the big important point I want to make here, guys, is the following. That if you take a number bigger than 2, if you take a number bigger than 1 and you multiply it by itself, the result is bigger. And the more you times that number by itself, the bigger the result gets. Well, let's take a number that's even bigger than 1, than the number 2. Let's take the number 5, for example, and multiply that by itself. We're going to take 5 and we're going to square it. We get 25. Let's multiply it by itself even more and see what the trend is, guys. Well, I hope you agree 5 cubed is 125. How about 5 to the 5? That's already a really big number. That's 3,125, guys. But now let's take 5 to the 10. That is 9,765,625. So check it out, guys. When you take a base over here, 5, that's even bigger than 1 than 2 is, then when you multiply it more by itself, it gets really enormous. The more you multiply it by itself, the bigger the results get. But now we've seen the number 2 and the number 5 multiplying by itself. How about a number that is just a little bit bigger than 1? A tiny bit bigger than 1, guys. Let us take this number, the number 1.1, okay? That is a small bit. Oh, not even, actually, I'm even going to take a smaller number than that, guys. I'm going to take 1.01. Guys, 1.01 is 101 out of 100, okay? So that's 1/100th more than 1. So we're going to take this and we're going to times this by itself a certain number of times, and we're going to see what happens with the result. Is the result bigger or smaller than what it used to be? And if we times it by itself even more, does the result get bigger or does the result get smaller? So 1.01 squared, that ends up being 1.0201. So it's bigger than what it started out as. Well, how about if we take this and multiply it by itself even more times? 1.01 cubed, 1.01 to the power of 5, 1.01 to the power of 10. Well, we get the following answers. 1.03 ... We get the answer of 1.05 ... And over here, we'll get the answer 1.10 ... over there. So even though 1.01 is only a tiny bit bigger than 1, when we times it by itself, the result is bigger than what we started with, and the more we times it by itself, the bigger the result, okay? So now, guys, when comparing all of the above results, it should be clear that we can make the following conclusions. When a positive number n is multiplied by itself and 0 is less than n is less than 1. For example, guys, this is the example we had where n was equal to a half, or n was equal to 1/10, or n was equal even to 99 over 100, okay? So when n is greater than 0 but less than 1, then the more we multiply n by itself, the smaller the result. The smaller the result. But when n was equal to 1, well, then irrespective of how many times we multiply n by itself, the result will be 1. But when n was greater than 1, the more we multiply n by itself, the bigger the result. Now, how in goodness name does this relate to what we've been doing over here? How does this explain what happens when we took b is equal to 2 over here and then drew the graph of b is equal to a half instead? Well, please notice, guys, that b here is a positive value. Here, b is a positive value that is less than 1 but still greater than 0, whereas b here is a value that is simply greater than 1. Okay, is that reminding you about something? Well, let's go down over here and see how these are connected, right? The above conclusion helps explain the effect of changing the parameter b in y equals a times b to the x from 2 to a half. Remember, as x increases, so does the number of times we multiply the parameter b by itself. Think about it, guys. In y equals a times b to the x over here, okay? That exponent x, this exponent right over here, that is telling you how many times you multiply this parameter b by itself. So if x gets bigger, you are telling the b to multiply it by itself more times. Now, hence, we saw from our efforts above that when a is positive, so when a is positive and b is greater than 1, i.e., for example, in our example, b is equal to 2, then if x increases, then y increases exponentially, guys. It increases exponentially because if x increases, then b is being multiplied by itself more times, and if b is greater than 1, the result, which is y, will keep getting bigger and bigger and bigger and bigger, and it will increase exponentially, and the function will have an increasing graph, guys. It will be an increasing graph, okay? This is for when a is greater than 0. But how about over here? How about if 0 is less than b is less than 1? So b is positive but less than 1. For example, when b was equal to a half. Well, if x increases, then the number of times we are multiplying the base by itself increases, and the result will get smaller. Y will decrease exponentially, guys. Decrease exponentially over there, and the function will have a decreasing graph as a result, a decreasing graph. Now, I need to point out once again, guys, that this is very specifically for when a is positive. These conclusions are made when a is positive, which obviously means that we should now investigate the effect of the parameter b for negative a values. So let's move on to those negative a values, guys. Okay, now let's consider the two functions that have a equal to -1. We know from our work on the previous pages that the asymptote for y is equal to -2 to the x is the x-axis, in other words, y equals 0, and the table of values is as follows. So please, guys, check out what we're doing over here. We are going to check out the graph where a is now equal to a -1, q is still equal to that boring 0, but we are going to compare this graph where b is equal to 2 to this new graph that we're going to get for the function with equation y is equal to -1/2 to the x, okay? And this is obviously where a is still equal to -1. We're obviously are looking at what the effect of b is now for these negative a values, okay? Q is still equal to 0, but now the new b value here is 1/2. Okay, we're seeing what that changing b to 1/2 will do when we have a negative value over here now in the equation of our function. Okay, so let's complete this table of values using the equation y equals -1/2 to the x. Now, you smarty pantsers over there, yes, once again, we could fill out this table of values really easily. Why could we fill it out so easily? Because these y values are nothing more than the negative version of y equals +1/2 to the x. Let's look up here, guys. Where is that? Where is that? Where is that? Here we go. Y is equal to +1/2 to the x. I know that I can just take all these y values, slap a minus in front of them, because that is, after all, what happens when we change a from +1 to -1. You're just taking these results, timesing them by -1, turning them into the negative versions of themselves. Where are we? Here we are. Okay, so that's what I'm going to do, guys. I'm going to fill out these values really quickly. Okay, so there are our negative versions of the y values, okay? We don't have to manually calculate them, guys. And before now taking these points and drawing the graphs, it's important to note that the function of y is equal to -1/2 to the x also has an asymptote at the x-axis, in other words, at y equals 0. In other words, y equals 0 will still make this function this equation, rather, a false statement with no solution for x. Let me just quickly demonstrate that once again, guys. If we let y equal 0, then we get 0 is equal to -1/2 to the power of x. If you want to, you can choose to divide both sides by -1 like this, because boom, boom, that's y over there. And thankfully, 0 divided by -1 is still just 0, and you end up with 0 is equal to 1/2 to the power of x, guys, which is a false statement. There is no solution for x, not real or non-real here, guys, because there's no possible x that you can take 1/2 and put that to the power of the x value that will give you 0. The graph does not exist for y equals 0, so that asymptote is still at the x-axis, y equals 0. Okay, but that aside, let's take these points, let's plot them, let's connect them, let's draw the graph, and then we'll be able to see what that value of b is equal to 1/2 does to the graph when we have a negative value for a. So let's do this. Okay. And there's our sexy graph for y is equal to a -1/2 to the x in comparison to y is equal to -2 to the x, which was already plotted for us so that we didn't have to waste our time drawing it all over again. So let's see what happened when we changed that b is equal to 2 to b is equal to 1/2, a value that is less than 1 in comparison to a value that is greater than 1 over there. Once we have plotted the new graph, it should be clear that the graph of y is equal to -1/2 to the x is an increasing function in comparison to the decreasing function of y is equal to minus 2 to the x. Oh, now that's interesting because this is opposite to the result we got when a was equal to positive 1. This change in result is because of how the negative a parameter interacts with what we've learned about the b parameter, guys. Okay. Hence, we can make the conclusion that when a is less than 0 and b is greater than 1, for example, when b is equal to 2, then if x increases, then y decreases exponentially, guys. It decreases exponentially like that. And the function will have a decreasing graph, okay? That's opposite to when a was greater than 0, just like the next conclusion was opposite. So if a is less than 0, but b is greater than 0, but less than 1, for example, if b was equal to a half, like we had over here, then we saw that if x increases, then y increases in an exponential way, increases exponentially, okay? And the function will have an increasing graph. So this time, these are the conclusions that we can make about the parameter b for the a values that are negative. And with that said, guys, we can now summarize what we have learned about the influence of parameter b, okay? Parameter b on the shape of the exponential functions graph with equation y is equal to a times b to the x. In other words, when q is equal to 0, in the equation y is equal to a times b to the x plus q, with the restriction that b is greater than 0. B is always going to be greater than 0, okay? That is, by definition, it must be greater than 0. But the big point I'm just trying to make here, guys, is that the following conclusions that we're about to make are specifically for when q is equal to 0 in this equation over here. Okay, so let's see what we can conclude about the effect of parameter b. Well, it's the interaction between parameters a and b that determine whether the graph is an increasing or a decreasing function. Let me show you what we have over here, guys. Okay, when we have a greater than 0 over here, we know that the graph will live above the asymptote over here. So here will be our asymptotes. I think you can agree. Here are our asymptotes. And when a is greater than 0, we know that our graphs will live above the asymptotes, okay? The graph will live above the asymptote. That's what we previously saw and what we concluded about the a parameter. But now we've seen that when a is greater than 0 and when b is, for example, greater than 1, a positive value greater than 1, we looked at specifically when b is equal to 2, we saw that the graph made this shape over here. It went whoop, boom, like that. It was an increasing function. As x increased, then y increased exponentially, and that's because of what happens when you take a value that is bigger than 1 and multiply it by itself many times. The more you multiply it by itself, the more it gets over there. Okay. Whereas when the b value was between 0 and 1, so it was like a fraction value that was less than 1, but still obviously positive because it has to be, we ended up with a function that looked like this. Wee, 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 wee. Boom, over there like that. Okay, so that means that we ended up with a decreasing function, and that obviously happened because of what happens when you take a b value that's less than 1 but still positive and you multiply it by itself many times. The more you multiply it by itself, the smaller the result gets. So when b is greater than 1 and a is greater than 0, you end up with an increasing function over here. In comparison to when b is between 0 and 1, you ended up with a decreasing function over here. But how about when a was less than 0, when a was negative? Well, you had your asymptote, and you knew that when a is negative, the graph lives below the asymptote only. It only lives below that asymptote right over there. And we saw that when b was greater than 1, we didn't have an increasing function anymore. Now we had a decreasing function like that. In comparison to when b was less than 1, but obviously still greater than 0 because it has to be, we ended up with an increasing function just like this. Now, this poses a problem for us, guys. Why is this a problem? Because it's very difficult to remember all of this. I mean, do we always have to remember that if b is greater than 1, then it'll only be an increasing function if a is greater than 0, but it'll be a decreasing function if a is less than 0, and when b is between 1 and 0, blah, 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 blah. Do we have to remember all that? Well, no, we don't have to, because there's actually a way that we can generalize about what b does to the graph of an exponential function. Okay, we can generalize a rule for when b is greater than 1, and we can generalize a rule for when b is between 1 and 0 over there. And look how we are going to do that, guys. So check this out. So this is how I'm going to do this, guys. When b is greater than 1, if b is greater than 1, please notice something. As x increases, the y value will. What does the y value do for both of these graphs over here when b is greater than 1? In other words, irrespective of whether a is positive or negative, what is the same about these two graphs when it comes to the y values? Well, let me remind you about this first, guys. For all the graphs we've done so far, the asymptotes have always had the equation y equals 0. In other words, they've always been the x-axis, okay? Now, please notice that as x increases, in other words, as we go to the right, please notice that the y values of these two graphs will get further away from the y value of the asymptote. Check it out, guys. Yes, this graph is going up and away from the asymptote. Yes, this graph is going down and away from the asymptote. But I think you can agree that the y value of the graph is getting further away from the asymptote when b is greater than 1, irrespective of whether a is positive or negative over here. So that's the conclusion we can make for b greater than 1. If b is greater than 1, as x increases, the y value will get further away. It will get further away from what? From the y value of the asymptote, guys, okay? In other words, as x increases, the graph will get further away from the asymptote, okay? So that is a conclusion that we know that we can make about b is greater than 1. That's what we know will happen to the graph. It will either be increasing or decreasing, but either way, as we increase x, it'll get further away. It'll shoot to the stars or it will shoot to the depths of the ocean. Okay. Now, conversely, guys, we can say that if b was between 1 and 0, so if it was some kind of positive fraction value that was less than 1, guys, then we can see that as x increases, what does the y value do this time? Well, once again, guys, so far we've only dealt with y equals 0 as our asymptote, y equals 0 as our asymptote, but this time as x increases, please notice that the graph gets closer and closer to the asymptote. It gets closer and closer to the asymptote, irrespective of whether a is positive or negative, okay? In other words, the y values of the graph get closer to that y value of the asymptote over there, okies. Do you see that? Let's write that conclusion down. If b is between 1 and 0, as x increases, the y value will get closer to the y value of the asymptote, guys. Whoa, Mr. Marie, where is the letter G in asymptote? I ask you, Mr. Marie. In other words, as x increases, the graph will get closer to, whoopsie, Mr. Marie, once again, you're trying to mix up words there, to the asymptote, okay? So there is the very helpful conclusion we can make about b that doesn't rely on us knowing what's going on with the a parameter. If we see b is greater than 1, it's going to go away from the asymptote as x increases. If b is between 0 and 1, it's going to go closer to the asymptote as x increases. And then depending on your a value, guys, then you will see if it's increasing or decreasing. Okay. Hey, that's 2 parameters down. 1 more to go, guys. We've done so well so far. Let's keep it up. That last parameter is parameter Q, and we're going to now investigate the effect of parameter Q. To identify what happens to the shape and or position of an exponential function's graph when we change the value of Q, we are going to draw the graphs of 2 new exponential functions that have 2 different Q values. We will then compare these graphs to each other and the graph of the classic function y equals 2 to the x, which will then allow us to make conclusions about how the value of Q affects the shape and or position of an exponential function's graph. Now, we know from our work on the previous pages that the asymptote for y is equal to 2 to the x. This is the classic Okie, guys. Y is equal to 2 to the x, where a is equal to 1, b is equal to 2, and very importantly now, q is equal to 0 is the x-axis. In other words, it is y equals 0. Y equals 0 is the asymptote for q equals 0. We'll see how that plays out. And the table of values is as follows. Here's the table of values for the classic. We should be well familiar with it by now. Now what we're going to do is we are going to complete the table of values using the equation y is equal to 2 to the x minus 1 over here. What are our parameters here? Well, it shouldn't be a surprise that a is still just a positive 1, that b is just a positive 2, exactly the same as what we have here. But now q is a different value. Q is now equal to minus 1 over here, guys. And that should make sense. We're investigating what the parameter q does. Let's calculate a few points over here, guys. How about we calculate what y is when x is equal to minus 4? Well, y will equal to 2 to the minus 4, 2 to the minus 4, minus a 1 over there. We know that 2 to the minus 4 is 1 over 16, and then we minus 1 from 1 over 16, and we end up with minus 15 over 16 over there. So y is equal to minus 15 over 16 when x is equal to minus 4 over there. Let me just quickly do that. Okay, and let's calculate another value or 2 manually. How about our good old friend when x is equal to 0 over here? What will y equal? Y will equal 2 to the 0 minus 1. 2 to the 0 is 1. 1 minus 1 is equal to 0. Now that is interesting, guys. Look at what we have over here. We have y equals to 0 as an actual answer for when we subbed in an x value. Now, previously, the y equals 0 line, the x-axis, was always off bounds. It was always an asymptote. But now, we have y equal 0 in an actual point on this graph, guys. The point 0, 0 exists on the graph. In other words, this graph goes through the origin. In other words, the origin is a y and an x intercept for this graph. Ooh, what's happening here, guys? What's that q equals minus 1 doing here? Okay, well, let's calculate maybe one more value for y manually. When x is equal to 3, y is equal to 2 to the 3 minus a 1. 2 to the 3 is 8. 8 minus 1 is 7. So y is equal to 7 when x is equal to 3 over there. Okay, and with those values done, let me just quickly fill out the rest of the values over here, guys. Okay, so there we go, guys. I have filled out all of our y values over there, including the decimal versions, if you guys find it easier to plot the point minus 3 minus 0.875 in comparison to minus 3 minus 7 over 8. And now, let me first address you smarty pantsers out there who may have noticed the connection between y is equal to 2 to the x, where q was just equal to 0, versus, well, the connection between y is equal to 2 to the x and y is equal to 2 to the x minus 1. Now, please notice that every single time, guys, we calculated the y values starting in the same way. We had to take 2 and put it to the power of the x value. But after we got that, we minused 1 from that. So it really should not come as a surprise at all that every y value in our original graph, where q is equal to 0, is simply 1 more than the new y value that we had over here. And that's because every single time we calculated 2 to the x, we just minused a 1 before getting our y value, guys. So check it out. Here are the original y values. Now that we are minusing 1 from 2 to the x, it shouldn't be a surprise. Whoop! Minus 1 there, guys. The y used to be 2, now the y is 1. The y used to be 8, now the y is 7. The y used to be 1 over 8, now the y is minus 7 over 8. So that q is equal to minus 1 just resulted in all the y values being 1 less than what they used to be. Okay, we're going to see what effect that has on how the graph actually looks now as well. But at this point, it's important that we notice that the asymptote for y is equal to 2 to the x minus 1 is no longer at the x-axis, i.e. y is equal to 0. It's no longer there, guys. For example, let's sub y equals 0 into the equation and see what the result is. Now, we should already know what to expect, guys, because we know that when x equals 0, y is equal to 0. So therefore, if y is equal to 0, then x equals 0. But let's just drive the point home over here, guys. We're going to sub in y equals 0 into the equation. What was the equation? The equation was y is equal to 2 to the x minus 1. So I am going to go ahead and sub y equals 0 here. We would get 0 is equal to 2 to the x minus 1. I hope you agree with me, guys, that we would probably want to take this minus 1 over to the other side where it would become a plus 1. In other words, we're basically just adding 1 to both sides of the equation here. What do we get? We get 1 is equal to 2 to the x. Oh my goodness, I have an exponential equation where I'd really like it be in the form a to the m is equal to a to the n, which can allow me to make the conclusion, therefore m is equal to n over here. And I can do that, guys, because guess what I can change 1 to? I can change 1 to 2 to the 0, okies. So this equation will become 2 to the 0 is equal to 2 to the x, and therefore I know that x is equal to 0 when y equals 0 was subbed in over there. Oh, what do you know? Okay. And basically, guys, remind yourselves, what are we determining when we let y equal 0 in the equation of a function? We're determining the x-intercept. This tells us that 0, 0 is the x-intercept, guys, just like we saw earlier. Now, the above result tells us that there is a real solution for x when y is equal to 0 in y is equal to 2 to the x minus 1. In other words, we now know that the graph of y is equal to 2 to the x minus 1 exists for y equals 0, which obviously means that there cannot be an asymptote at the x-axis. In other words, y equals 0 anymore, guys. If the graph exists for y equals 0, then there can't be an asymptote there anymore. In fact, even though a is greater than 0, there are now some negative values for y that we can sub into y is equal to 2 to the x minus 1 that will give us a real solution for x. That's very different from before, guys. Before, when q was just equal to 0 and we had a greater than 0 on top of that, we never got negative values for y. But now that we've changed the value of q, we're getting negative values for y even though a is greater than 0. So for example, guys, let's sub in y is equal to minus 1 over 2 into the equation and see what the result is. Okay, there's our equation. Let's sub in y is equal to minus 1 over 2 there. Minus 1 over 2 is equal to 2 to the x minus 1. Hope you agree with me, guys, that in our attempts to solve for x here, we're going to take that minus 1 over to the other side. In other words, we're adding 1 to both sides over here. And what do we get left with? We get 1 over 2 is equal to 2 to the x over there. This is basically 2 to the invisible 1 on the bottom of this fraction over here. So I hope you're thinking, I know that exponent law, guys. I can take 1 over a to the n and say that it's equal to 1, say that it's equal to a to the minus n over there. So what are we going to do over here? We are going to go ahead and say that 1 over 2 is 2 to the minus 1, basically, which equals 2 to the x. We did this because now we can make the conclusion, therefore, x clearly must equal minus 1 over here. So basically this means that there's a point minus 1 minus a half that exists on the graph of this function even though a is greater than naught, guys. What is q doing to this function? Now, once again, the above result tells us that the graph of y equals 2 to the x minus 1 exists for y is equal to minus 1 over 2, which means that we have still not found the asymptote of the function, okay? Now let's sub y equals minus 1 into the equation and see what the result is. Okay. We're subbing in y is equal to minus 1, which just so happens to be the value of q over here, guys. Remember what our value of q was? Q was equal to minus 1 over here. And remember up here, guys, when we saw that q is equal to naught, we still had the asymptote at y equals naught. Oh, I wonder what will happen now when we sub in q is equal, when we sub in y is equal to minus 1, which happens to be the q value. Let's see what happens here, guys. So now we would have minus 1 is equal to 2 to the x minus 1. In an attempt to solve for my unknown exponent x over there, I'm once again going to try and get the equation into the form a to the m is equal to a to the n, just like we had over here. So it should come as no surprise once again that we're going to take this minus 1 over to the other side where it would become a plus 1. In other words, we're adding 1 to both sides, guys, and we end up with naught is equal to 2 to the x. Guys, it's our false statement. It's the equation that has no solution for x, not real or non-real. There's no value for x that can make this true. This is impossible. This above result shows that there is no solution for x when subbing y equals minus 1 into y is equal to 2 to the x minus 1. What do you know? When we sub that q value into the equation of the function, we end up with that false statement, which shows that the asymptote is at y equals that minus 1, what that q value happened to be. In other words, the equation becomes a false statement at y equals minus 1, and hence we have revealed that y equals minus 1 is our new asymptote. How convenient. It's the same as the q value there. Okay, but I'm getting ahead of myself, guys. I'm being naughty. I'm revealing what's happening here. And before I start making any conclusions, guys, I rather want to check out what happens now to a graph if we change the q value again. Previously, we had q equals minus 1. Now we're going to choose a q value that is positive. And we're going to fill out this table of values using this equation. It should come as no surprise, guys, that a is still just equal to a positive 1 here. B is still just equal to a positive 2 here. We don't want to change the a and b value because we're changing the q value to see what effect that has. Now q is equal to a positive 3. Let's see what our y values will now be. And yes, to you smarty pantsers out there saying that, Mr. Marie, why are you wasting time calculating these values manually? Look at that plus 3, Mr. Marie. What is that going to do? You're just going to add 3 to the old results you got for 2 to the x. That's how all these y values are going to go. You're going to sub an x, you're going to do 2 to the x, and after you get that, you're going to add a 3 to it, Mr. Marie. Yes, you smarty pantsers. Yes, you're all smart and stuff. Respect to you. I'm actually going to calculate some of these manually just to really show you, to drive that point home. What is y equal to when x is equal to minus 4? Y would be equal to 2 to the minus 4, exactly as we've done a million times. Whoopsie. But now we're going to add a 3 to the result. 2 to the minus 4 is 1 over 16, and we're going to add 3 to that result. And when you add 3 to that result, you end up with 49 over 16. So that's a 49 over 16, and if you find it easier to plot, guys, that's 3.0625. What do you know? 3 units more than what it used to be when q was equal to naught. Okay, well, let's do a couple more values manually, maybe. How about this okie over here? What did this used to be with the classic version when q is equal to naught? This used to be 1. I wonder if it will now be 4. 3 more than what it used to be. Well, let's see, guys. Y would equal to 2 to the naught over there, plus 3. Oh my goodness, what do you know? 2 to the naught is 1. 1 plus 3 is 4. Okay. Well, last but not least, why don't we just calculate this okie manually over here? Y would equal 2 to the 3. We've done it a million times, but now we would add 3 here. 2 to the 3 is 8. 8 plus 3 is 11. What do you know? 3 more than what it used to be with the classic function. And so it goes, guys. I don't even need... Whoopsie, Mr. Marie, what have you done? I think that's incorrect over there. There we go. I don't even need to speed up all my writing over here, it's so easy to figure out all the y values that they should be, including their decimal versions of themselves, guys. So let me just quickly get through this. Oopsie, that's not right over there. Is it, Mr. Marie? That is definitely not right. That would be over there. Oh, no, it was right. I was just being a chop. Okay, so that's 3.5 over there. Okay, there we go. So what do you know? 3 more than what the y values were for the original classic function. Now, once again, guys, it's important that we notice that the asymptote for y equals 2 to the x plus 3 is no longer at the x-axis, i.e. y is equal to 0. For example, let's sub y equals 0 into the equation and see what the result is. Okay, so our equation is y is equal to 2 to the x plus 3. Y was equal to 2 to the x plus 3. We're going to let y equal 0 now. So we would now have 0 is equal to 2 to the x plus 3. In an attempt to get 2 to the x by its lonesome on one side, I would take plus 3 over to the other side. It would become minus 3. In other words, I can think of it as though I'm minusing 3 from both sides. Either way, we end up with the following, guys. We end up with minus 3 is equal to 2 to the x. Now, I know what you're thinking. You're thinking there's no x value that can make 2 to the x equal to a negative number. Well, there's no real value. But guys, while it may look like subbing y equals 0 into y is equal to 2 to the x plus 3 results in an equation where there is no solution for x, there is technically a non-real solution for x. This does not mean that the graph exists for y equals 0. It simply means that we have yet to find the y value for which the equation is a false statement. In other words, we have yet to find the y values that will give us the asymptote of our new exponential function over here, guys. So this has no real solution for x, okay? We're looking for the equation which has no solution for x at all. That would be the y value of our new asymptote, okay? And guys, something else that's important to notice is that even though a is greater than 0, even though a is a positive 1 over here, there are now some positive values for y that we can sub into y is equal to 2 to the x plus 3 that will result in an equation that has non-real solutions for x. Think about it, guys. Previously, when a was greater than 0, we could take any positive value for y, sub it into the equation of the function, and we would get a real solution for x. But now that this q value here, now that we have this q value of plus 3 over here, okay, q is equal to a positive 3. Even though a is greater than 0, we're getting some y values that when subbed in create non-real solutions for x. For example, let's sub y equals 1 into the equation and see what happens to the result. So 1 would equal to 2 to the x plus 3, 2 to the x plus 3. I hope you agree with me, guys, that if we tried to solve this, we would take 3 to the other side. In other words, we're minusing 3 from both sides. And this results in an equation that has minus 2 is equal to 2 to the x. Now, yes, guys, it looks crazy, but there is technically a non-real solution. There's just no real solution for x over here. So once again, we have still got to find the y value of the asymptote. We have still not found it. We have not found that y value that makes the equation completely false. Now, finally, let's sub y equals 3 into the equation. Y is equal to 2 to the x plus 3 and see what the result is. Do you see what we're doing here, guys? We're making y equal to 3, which just so happens to be the same value of my q parameter over there. I wonder what's going to happen here, guys. Well, we would end up with 3 is equal to 2 to the x plus 3. In an attempt to solve for 2 to the x, we would take this plus 3 to the other side. In other words, I was minus both sides from 3. And what do we get left with, guys? We get left with 0 is equal to 2 to the x. Guys, check it out. It's our false statement. There's no value for x that could ever make this equation true. No solution for x, okay? The equation above has no solution for x when y is equal to 3. In other words, we have finally found the y value for which the equation becomes a false statement, and hence the y value of the asymptote for y equals 2 to the x plus 3. What do you know, guys? we found our new asymptote, and it just so happens to be y equals the value that q was over here. I wonder if that's a pattern. Okay, so now that we've finally found the asymptotes for our two new graphs, one where q is equal to -1 and the other one where q is equal to a positive 3, we will now draw these two new exponential functions on the Cartesian plane on the next page, which already includes the graph of y is equal to 2 to the x. Remember, guys, this is one where a is equal to 1, b is equal to 2, and that q value is equal to 0. So we're going to be able to compare q is equal to 0 to q is equal to 3 to q is equal to that -1. Where's that -1? Here's that -1. Okay. So this is where q is equal to -1. And now we can compare all three of those by plotting them on the same Cartesian plane and seeing what the result is. Hey, and there you have it, guys, our three new graphs. I have to scroll up and down for you to see all of them at once. But guys, we have our original purple oak there where q is equal to 0. And what do you know? When q is equal to 0, the asymptote was y equals 0. I wonder if that was a pattern. Well, when q is equal to a positive 3 with my green graph, we had q is equal to 3 and the asymptote was y equals 3. What do you know? And finally, when our q value was equal to -1, we had an asymptote at y is equal to -1, guys. Not only that, but look at the graphs themselves, okay? No matter which point I point to on my original graph where q is equal to 0, if I go to its equivalent point on y equals 2 to the x plus 3, you should notice that it is 3 units above, whoop, boom, 3 units above what it used to be. It used to be here, now it's whoop, boom, 3 units above. It used to be here, now it's whoop, boom, 3 units above. So, having q equals 3 looks like it's taken the whole graph, including the asymptote, and gone whoop, boom, 3 units up like that. In comparison to when y is equal to -1, then what happened, guys? Well, rather when q is equal to -1, then what happened? Well, every single point that was on the purple graph moved 1 unit down, moved 1 unit down, moved 1 unit down over there, and that included the asymptote. So the asymptote used to be at y equals 0 when q was equal to 0, but now the asymptote is at y is equal to -1 when q is equal to -1. We went 1 unit down there. Do you see what that q value does, guys? That's why when we changed the q value, the y equals 0 wasn't the asymptote anymore. In other words, that's why when we changed the q value, we suddenly had a y-intercept over here for one of the, an x-intercept for one of the graphs, because the asymptote was no longer on the x-axis. Okay, so once we have drawn the two new graphs, it should be clear that the q value shifts the graph up or down relative to y is equal to 2 to the x, including the asymptote. The q value shifts the graph up or down relative to y is equal to 2 to the x, including the asymptote. More specifically, when q is equal to -1, the graph is 1 unit below y is equal to 2 to the x, whereas when q is equal to positive 3, the graph is 3 units above y is equal to 2 to the x. Furthermore, we should notice that the y values of our asymptotes correspond directly to the values of the q parameters in our functions. We've noticed that over and over again, guys. Finally, it is valuable for us to notice that the graph with q less than 0 now has an x-intercept. Interesting. Now, that's not necessarily always going to be the case, guys, because we're not always going to have graphs that point up, for example. Sometimes we're going to have graphs that point down. So it's not like we can make a conclusion that for q is less than 0, we'll always have an x-intercept. We're going to see about that a little bit later. Now, before we summarize what we have learned about the influence of parameter q on the position of an exponential functions graph with equation y equals a times b to the x plus q, it is also valuable for us to acknowledge that the q parameter will have the same effect on exponential functions that have a less than 0 with the exception of what we had over here, okay? With the exception of that conclusion, which I will point out a little bit later, guys. Okay, so we don't have to investigate what Q does with graphs with a less than naught because it will have the same effect. It will shift the graphs up or down depending on the Q value. And with that said, guys, let us summarize the effect of parameter Q on our exponential graph. Now, please remember here, guys, that the conclusions we make about these Q values are going to be relative to Q is equal to naught. Okay, I'll show you what I mean by that just now. If we see that Q is positive, in other words, if Q is greater than naught, then what is the effect of parameter Q? Parameter Q will shift the graph and the asymptote, guys, shift the graph, including its asymptote, Q units up in comparison to when Q is equal to naught, relative to when Q is equal to naught. So let me show it to you like this, guys. When Q is equal to naught, okay, then we will have an asymptote where y is equal to naught will be the equation of the asymptote. And let's just, for example, say we had this exponential graph over here. Okay. Now, if we then change Q from being equal to naught to Q being greater than naught over here, then everything in this graph will shift Q units up. So in other words, our asymptote will now be at y equals Q, because this y equals naught would have gone whoop, shifted Q units up like that, and we would now have y equals Q over there, and this graph will be whoop, shifted Q units up like that, and so we will have the graph up here now. So that is what Q does. If Q is positive, it shifts the graph Q units up, shifts the graph Q units up in comparison to when Q is equal to naught. So in other words, relative to Q equals naught. How about if Q is negative? In other words, if Q is less than naught? Well, relative to Q equals naught, when Q is negative, that will shift the graph. It shifts the graph. Which direction now, guys? Shifts the graph Q units down. So for example, guys, if we had this value over here, or this asymptote over here, which would have the equation y equals naught, because our Q value was equal to naught. Our Q value is equal to naught, hence our asymptote would be y equals naught. And let's pretend that this was our exponential graph over here. Then, if we suddenly had to make Q less than naught now, Q less than naught now, what would happen is that the whole asymptote, boom, would shift Q units down to become the equation y equals Q. Yes, y equals Q, not negative Q, guys. Y equals Q. Because if Q is negative in the equation, you would just take that negative value, whoop, and put it right over there. So you would have y equals whatever that negative Q value is. Okay, so the asymptote moves Q units down just like the graph would move Q units down. Okay, whoop, boom, Q units down. So that is the effect of Q. Shifts up or down depending on if it's positive or negative, and it shifts everything up or down, guys. Wow, there we go, dudes. That's 3 out of 3 parameters done. And with 3 out of 3 parameters done, we can now summarize the properties for y is equal to a times b to the x plus q. In other words, we can make our summary for the whole equation now, not limiting ourselves to, oh, this conclusion is only for when q is naught, or when a is positive, or when a is negative, etc., etc. We're now going to make a summary for what all of these parameters do simultaneously to the graph. Okay, we're going to fill this out together. So, now that we have fully explored the effect of parameters a, b, and q on the shape and position of the exponential functions graph, guys, it is important that we summarize the properties we can expect for the graph with equation y is equal to a times b to the x plus q. So here's our overall summary. Properties of a graph with equation y is equal to a times b to the x plus q. What can we expect? Well, when a is greater than naught, that is when we will get graphs that live above the asymptotes, okay? When a is greater than naught, you will get graphs that are above the asymptote, above the asymptote, like that. Whereas over here, this is where you have a less than naught, and it will result in graphs that are below the asymptote, guys. So as soon as you see a negative a value, you should tell yourself, oh my goodness, I know that my graphs are going to be below the asymptote. As soon as you see a positive a value, you should say to yourself, oh my goodness, I know that my graphs are going to be above the asymptote. Okay, but now how about parameter b? Remember that general conclusion we made for parameter b, guys? Well, that conclusion was the following. Firstly, since we know that b has to be greater than naught, okay? It has to be a positive. It can never be a negative. Since we know that, the two categories for b is not b greater than naught or b less than naught. B can't be less than naught. Our two categories for b are b values that are between 1 and naught and b values that are greater than 1. Fraction values for b or b values greater than 1. And when we saw that we had b values that were between 0 and 1, what did we see, guys? We saw that the graph gets closer to the asymptote as x increases, okay? So where shall we write this? Let's write it maybe a little bit up here like this, okay? So for when b is like this for these two graphs, we know that as x increases, we know that the graph gets closer to the asymptote, okay? Getting closer to that asymptote. Whereas if b is greater than 1, we know that as x increases, what happens, guys? As x increases, the graph gets further away, from the asymptote. How sad. Further away from the asymptote over there. Okay, so these two graphs are what we can expect when b is between 1 and 0. These two graphs are what we can expect when b is greater than 1. And the a and the b parameters then combine to create situations that we have over here. So if we have a greater than 0 and b between 0 and 1, we will end up with that decreasing function over here. Whereas if a is less than 0 and b is between 1 and 0, then we will end up with an increasing function over here. Whereas it's sort of the opposite over here, guys. Here we end up with an increasing function when you have a greater than 0 but b greater than 1, whereas here you end up with a decreasing function when you have b greater than 1 but a less than 0 over there. And this is all in comparison to the asymptotes that we have. Okay, there we go. So how about what we had over here? Well, what did parameter q do? Remember, relative to q equals 0. What do we know? We know that when q is greater than 0, the graph is translated, okay? Graph translated. Translated is a fancy pants word for shifts. Graph translated q units up. Whereas with q is less than 0, we saw that the entire graph was translated q units down in comparison to if q was equal to 0. Now, what did that mean for the asymptote? Well, guys, we know that for the asymptote, when q was equal to 0, the asymptote was always y equals 0. But as soon as we started changing the q values, the equation of the asymptote changed to those q values. In other words, the asymptote will always be y equals q. So let me go up here and drum that into your heads, guys. These asymptotes will always have the equation y equals q, y equals q, y equals q, y equals q. Whether or not a or b are positive, those asymptotes will have the equations y is equal to q over there. Let's keep going, guys. Ooh, okay, here's an interesting one. The x-intercept when q equals 0, okay? Remember when q equals 0, that means that y equals 0 was the asymptote, which means that the x-axis itself was an asymptote. So there was no x-intercept when q is equal to 0, and that's because the x-axis was, or will be rather, is an asymptote when q is equal to naught. However, when q is greater than naught, when q is greater than naught, that is when a graph is shifted which way, guys? It's shifted up q units. Think about it. When q is greater than naught, we found that the graph was translated q units up. Now, what does that mean for the x-intercept of the graph? Does that automatically mean we'll have an x-intercept? Does that automatically mean we won't have an x-intercept? Well, to make this conclusion, guys, let me remind you about the following. Okay, we have, let's just draw an x and y axes over here. I'm going to draw two x and y axes for you. Okay, bada bing, bada boom. Okay, and now what I'm going to do here is I am going to go ahead and draw two graphs where q is greater than naught. In other words, where the asymptote is going to be up from y equals naught. It's not going to be at y equals naught anymore. In other words, the x-axis, it's going to have shifted up. Boopity, 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 oops. So here's my y equals q now, with q greater than naught. Here's also y equals q over here, with q greater than naught, shifted up from the x-axis over there. Now, let me show you what happens if I had an a value that was negative versus an a value that was positive. If I have an a value that's positive, then I have a graph, for example, that lives only above the asymptote. Whereas if I had an a value that was negative, I would have a graph that only lives below the asymptote, like that. Oh, interesting, guys. Look what we have here. When q is greater than naught, then the whole thing shifts up q units. But if a is less than naught now, look how I have an x-intercept now. Whereas over here, please notice that with a greater than naught and q greater than naught, there's no x-intercept, guys. Okay, so what's the conclusion that we can make here? Well, the conclusion is when q is greater than naught, there will only be an x-intercept if a is less than naught, because it's a that's less than naught that will make the graph point downwards, hence go through the x-axis. Let's write that up as a conclusion here and give ourselves a bit of spashy McSpashy to actually write that down. Let's say goodbye to all this nonsense. Goodbye, 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 goodbye. Here we go. Okay, so when q is greater than naught, there is only an x-intercept if what, guys? Only an x-intercept if a is less than naught. Just like when q is less than naught, there's only an x-intercept if what? If a is greater than naught. Now, this can be really helpful because in the next lesson, Exponential Functions 2, you're going to be expected to draw these graphs. And at a glance, you'll be able to figure out, oh, does this graph have an x-intercept or not? Well, q is greater than naught, but a is less than naught. Oh, okay, yes, there's going to be an x-intercept, etc., etc. How about the y-intercept? Is there any conclusion we can make about the y-intercept? Well, yes, actually there is, guys. Check this out, check this out, check this out. Okay, so for our y-intercept, what do you do when you want to work out the y-intercept? You let x equal 0, don't you? You let x equal 0 to work out the y-intercept. What's the standard form of an equation for the exponential function? It's y is equal to a times b to the x plus q. Now look what's going to happen here, guys. If I let x equal naught, then I would have y is equal to a times b to the naught plus q. Hey, okay, a times b to the naught. B to the naught is 1, and 1 times a is just a plus q. So what this shows you is that no matter what a, b, or q is equal to, if you make x equals naught, you're going to end up with a plus q as your y value. In other words, the y-intercept will always be the coordinates naught and a plus q. So to work out the y-intercept literally by inspection, you can just take the a value and add it to the q value. Boom! You have your y-intercept right over there. So the y-intercept is always naught and a plus q. A plus q will be the y value of your y-intercept. Last but not least, how about domain and range? Well, guys, domain and range, we're going to learn a lot more about this in the lesson Applications of Functions 1, where we learn how to calculate domain and range for every single function. But just to summarize it here, domain are all the x values for which the graph exists. And if I just had to point out over here, guys, these graphs, they can go forever to the left, they can go forever to the right, forever to the left, forever to the right. In other words, they exist for every x value on the Cartesian plane. So what we write for domain is x is the element of real numbers. X can be any number for these graphs, okay? Another reminder, if you want to learn more about this, go to Applications of Functions 1. How about the range of these functions? Well, guys, a range is all the y values that the graph exists for. So if a is greater than 0, please notice that y only exists for y values that are more than q. In other words, for y values that are more than the asymptote value. Whereas if a is less than 0, the graph only exists below the asymptote. In other words, the graph only exists for y values that are less than the asymptote value. So what's the conclusion we can have for the range? Well, if a is greater than 0, then the range is that y is greater than whatever the q value is, whatever the value of the asymptote is. Whereas if a was less than 0 over here, then our conclusion for range is that range will always be less than that q value. And there you have it, guys. That is the properties of exponential functions of the form y is equal to a times b to the x plus q. Like I said, that is the most difficult function you do in grade 10 by a long shot, but don't worry, you made it through. Oh, there you have it, guys. I warned you that was going to be a bit of a longer lesson and that there were going to be a few bumpy parts to that ride, but we made it through. We are now experts when it comes to y is equal to a times b to the x plus q and what a, b, and q can do to the graphs of those exponential functions. Now, you will have noticed that there are no worked examples for this lesson. I think this lesson was already long enough as it is, but if you want to now practice working with exponential functions, you need to check out the lesson Exponential Functions 2 or Applications of Functions 1. In Exponential Functions 2, we learn how to draw an exponential graph without a table of values, which you will be required to do, and we learn how to determine the equation of an exponential graph, okay? But in Applications of Functions 1, we learn other stuff about exponential functions, such as working out the domain and range of any exponential function or working out the average gradient of an exponential function. But I'm getting ahead of myself because that's all in the future. This is now, and for now, we're done.